So there's no better timing to talk about batteries compared to now. So when I was invited, I was thinking, what do I want to share with you? When I was hired 13 years ago, coming to the faculty, and that was really the starting time. I learned myself and learned from my students. We taught each other all the way for 13 years until nowadays. These 13 years, you have seen many great things happen. Our phone integration is better and better. We see the drone is coming up. Even my two boys have a DJI to play with. We see Tesla cars everywhere in Palo Alto. And our parking lot at Stanford right here, you can see a big number right now. This is getting more and more. California has the requirement, we have the renewable of 50%. Just in several years, less than 10 years, it's about 7 years from now. So these all call for what's the idea for energy storage. The top row is for portable. The bottom row is stationary. They have different requirements, but they share with the common parameters right there. These are the parameters you are looking for. How much energy you store per unit weight or volume. For your phone, is this watt per liter that's more important. For your car, watt per kilo is more important. One is by volume, the other is by weight. The cost, when I started in 2005, the battery cost was $400 per kilowatt hour at the cell level. And it's going down so fast, I'm going to show you the next slide. Lifetime, how many cycles it can go through, and calendar life. If you don't use it, just let it sit right there. Can you let it sit for 10 years or 20 years? You can still use it. This is important, particularly for the car and for the grid scale. How fast can you charge it? Whether you can make it safe or not. These continue to be the questions you never stop asking until nowadays. Well, if you look at how the batteries work, well, let's come to the battery 101. You take a cylinder cell, that's in the Tesla car. You cut it open. It has this jelly roll. If you zoom in and look at this, you have copper foil, aluminum foil. Now people try to push the limit. In the copper foil, 5 micron, 7 micron, aluminum foil, less than 10 micron. And this is the battery separator, right? They're separating anode and cathode. Anode consists of these particles, as well as cathode. They can store lithium in their crystal structure. Once you charge your battery, lithium go to anode. Electrons also come to anode. They meet in the anode, that's in charge state. And in the discharge state, they go back to cathode, back and forth. Whether a battery can work or not, you need to deal with these issues. This determines a lot about how the batteries work, whether it's safe, how long can you use it for. And you need to move electrons. If you want to charge your battery fast, you better move your electrons fast. Ions diffusion. These also involve in ions squeezed into the crystal structure in and out. There will be strain associated with the crystal structure because there will be volume expansion taking place. And at the end, the interface, each of these particles sitting into organic electrolyte, they need to be stable. And the anode side particularly decompose the organic electrolyte and generate this cell passivation layer, so-called the SEI. This needs to be stable. That allows lithiums to come in and go out, but no electrons eventually stop the side chemical reaction. So with this basic structure, let's look at where we are right now. This is the existing lithium-ion batteries and where we want to be in the future. And when I started, I told you the cost was about $400 per kilowatt hour. Now it's $130 in the cell level. It's quite significant reduction of the cost. Energy density now roughly about 220. If you use cylinder cell, it's actually 250. When I started, it was only 150. There's quite a bit of improvement right there. But we wanted to go up to 500. If you have 500 watt per kilogram of batteries, basically a car you drive will go 500 miles. That's roughly the correlation. So that's it, 500 watt per kilo. You get 500 miles. You actually don't need more. Cycle life, now we are sitting at about 1,000 cycles. After that, you have 80% capacity. And the calendar life, about 7 years. We could use more. We would like to go to 10,000. We'd like to go to 25 years. So after you finish using your car in 10 to 12 years, you still have the battery still working. Ship it to electrical grid and use it for the grid. This has a significant impact on the cost. Charging rate 1 to 2 hours. Can you get down to 10 minutes? You have heard a lot of noise in the literature saying you can do actual fast charging. So probably 95% or more of the work is not believable yet. Because when they do fast charging, they put in tiny amount of materials on there. And doing a tiny cell, they say they can do less than 10 minutes or even 1 minute. But that's not trustable. I'm talking about here is the real usable cell. Can you do less than 10 minutes? That's still a very significant challenge right there. And then you need to be safe. We don't know how to solve the safety problem yet. We still use organic electrolyte. It can still be burned. So we know we made a lot of progress compared to 13 years ago, but we still have a lot of room to go. The outline of the talk today, I want to answer some of the questions and also allow you to see the opportunity right there. First one is how far the energy density can go. How much more energy can we pack in a given size of the batteries? The second one is, well, in order to make, can we make immortal batteries? Just never die. Then you need to understand the fundamental process inside the batteries. I want to highlight a new tool allow us to see particularly the interface of our batteries. I want to come to the battery safety issue. Whether it's hopeless, as long as you use organic electrolyte, your battery won't be safe anymore. Whether we have solution to solve that problem. And I also would like to talk about grid scale energy storage. At the end, the number 5 is very important. Well, given the resources we have, all this, the availability of different elements, lithium, cobalt, and do we have concern? And if we want to deploy electrical car, go to a large scale energy storage, do we have enough resources to do so? Let's look at the first one, how high the energy we can go. So it comes back to the very simple equation to look for a new chemistry. It's the energy equals to voltage multiplied by charge. You need to either need to increase the voltage or increase the amount of charge you store. And the voltage has a limit. You see the current lithium-ion battery allow you to sit at about 4 watt. 4.1, 4.2, 4.3, once you hit to 4.5, electrolyte is really not that stable, not mention the 5 watt. Right? The voltage is too high, decompose your electrolyte. So there's a limit right there. And the amount of charge you can store, you can have a lot of room to play with. So eventually you want to store this charge with that voltage holding right there using lightweight and small volume. In the past 27 years, graphite has been used as your negative electrode, that's anode. And it has this layer structure, lithium, intercalated into the graphite structure. This is the theoretical limit you can reach. We are about that limit right now. There's very little room, very, very little room you can play with. But if you use new materials such as silicon or metallic lithium to store lithium ion, your capacity is 10 times more. It's 10 times more. So we have a chemistry right there for you to have a lot of room to grow. For the cathode side, lithium cobalt oxide used in your cell phone, lithium manganese oxide, lithium iron phosphate. This has a 2-dimensional, 3-dimensional, and 1-dimensional crystal structure channel for you to store lithium. That capacity also has a limit. They are not that high. New materials such as sulfur become lithium sulfide, allow you to store also 10x. So this chemistry is really exciting. After about 10 years of research and explore broadly what type of chemistry they are attractive for the transportation for the grid scale. If you're looking for the chemistry that can have practical, I'm mentioning practical, not theoretical, high energy, this might be the pathway we have to follow. And nowadays still graphite combined with a nickel manganese cobalt oxide, that's here, XYZ, different ratio. And the maximum you possibly can reach is about 250 watt per kilo. And with silicon, replace graphite coming in, you get to 400. And metallic lithium coming in to replace silicon, you might get to 500. And then sulfur coming in, replace MMC, combined with lithium metal, you could reach potentially 600 to 800 watt per kilo. We have chemistry allow you to have a runway of 3x in a practical sense. But this could take 10, 15 years in a practical cell when you see this technology coming out. So the reason is the following. This is a slide I asked my student Ya Yuan to make. This is the relative volume change. I plotted in a way is a lithium versus the host atom, host lithium. You notice that the materials used in current technology is 1 lithium, 6 carbon. So lithium to carbon ratio is 1 to 6. Lithium cobalt oxide roughly use half of the lithium. The ratio is 1 to 6. Lithium iron phosphate is also about 1 to 6. The volume change right here is about 10% or less, very small. As soon as you store a lot of lithium into hosts, these different materials really start to show up. However, the amount of volume expansion you have increased tremendously. This is one of the fundamental reasons to use the high capacity material is so difficult. It caused the following problem. Past 27 years, we have stable hosts to host this lithium. New materials can store a lot more lithium, has the problem of chemical bond breaking. So many lithium and so many electrons coming in, store in the structure, you have the bond breaking. Atoms are moving all the time for these host materials. Very large volume structure change, big volume expansion. So you need completely new ideas. How do you handle the materials issue in order to make these materials workable inside your phone, inside your car? So my group started to work on this to tackle silicon problem. Silicon has 11x of the capacity of graphite. Volume expansion is 4 times. It causes breaking because it expands too much. And also the interface on each of the particle surface is not stable. How do you address that problem? It wasn't known. So let me show you this video. It's quite dramatic. This is the one, a silicon nanoparticles inside TEM. We are doing in situ measurement, charge up this particle with lithium. It's 800 nanometer in diameter to start with. And you see significant volume expansion. And after a while, this particle eats too much lithium. And it's going to get broken. And this breaking and cause the failure of the battery materials. The first time you charge out your battery, it's already dead. So that's a challenge we are facing. So using a technique like this, we could identify what's the critical breaking size. After you have the particles smaller than those size, they won't be broken anymore. 150 nanometer is about the size. And with this understanding, my group has been through 11 generations of design. And this was the first generation. We start from silicon nanowires They have small diameters, volume expansion can happen, but they don't break anymore. We solved the breaking problem. Indeed, this paper started the whole research field of using nanotechnology for energy storage, starting from this paper. We go to the core shell design, and using a stable core to stabilize the whole structure is getting better. Hollow structure design, so you can have interior hollow space and having more volume to relax the strain. And we have been through now 11 generations. Each generation, we try to solve one problem. And you can see this all stacking up, all this learning. Now start to build up the material design principle for industry to use, and eventually to solve the problem of volume expansion, breaking, and instability of a solid electrolyte interface. So this has resulting in companies, a startup founded about 10 years ago, now having the real batteries in the market, used in the phone, in the drone, soon will go into the electric car. And the energy density, 300 watt per kilo, the manufacturing line 1 design, and our China plant, and the line 2 reach about 400 watt per kilo. This is a lot more than what graphite anode can offer. So this is our manufacturing plant in Wuxi City in China. 2016, we have the whole board of directors visiting the plant, having a celebration. So this is going with high promise. This could go into the electric car in a big way. So what's next after that? I show you the roadmap. Eventually, we want to make lithium metal to work. In 2016, the White House announced the Battery 500 Consortium. This is a consortium under Department of Energy, providing $15 million for 5 years. Let's try to generate 500 watt per kilogram of batteries. The PNNL National Lab, together with Stanford Select, are the co-lead of this consortium. We have a very strong team of people from multiple institutions, try to address this challenge. Now we need to come to lithium metal, metallic lithium. I show you metallic lithium can potentially offer as an anode combined with nickel manganese cobalt oxide and with sulfur with a 500 watt per kilogram or higher energy density. And you look at half a century ago, and before I was even born, and lithium battery really started from lithium metal anode. However, it was too challenging. People didn't know how to solve the problem. That's because if you start from a lithium metal anode, it's so reactive with organic electrolyte. It forms an interfacial compound, SEI, right away. And then once you charge out your battery, you need to place lithium onto this lithium foil. There's no guarantee this interface will be flat during plating. You are going to change the surface topology. This will stretch your SEI layer, will make a crack or multiple cracks on the surface. This nuclear hotspot, you will grow this filament out of this hotspot. This filament grow longer and longer, can make the battery shorting happening, punches through the separator and make the battery catching fire and explosion. That was indeed a major challenge. You have seen past 10 years multiple battery incidents. Many of them are related to this lithium, metallic lithium dendrite growth, cause the battery catching fire. And then when you strip the lithium during discharge, there's no guarantee it will come from the tip. It might go to the bottom. Then you're going to cause this filament of metallic lithium detach from the underneath lithium foil. You use lithium metal very fast. The cycling efficiency is very low. You build up this so-called dead lithium, the battery also die very fast. So for the realistic battery, for unit area per centimeter square, you need at least 3 milliamp hour of capacity. That translates to 15 micron thick lithium metal. So every time you play lithium metal, you play 15 micron thick, you strip away, it goes back to 0. Then this 15 micron thick, and each layer is just too large for a battery cell to handle. We have summarized all this learning and this perspective paper in Nature Nanotechnology. We combine what people learned in the past 50 years and what we learned in our group. And we pointed to the community. We said the root cause of the problem is actually in the center. Outside is the surrounding phenomenon. The center problem is high chemical reactivity of lithium, coupled together with relative infinite volume change during plating and stripping up and down. This process makes it very hard to handle. So this causes all this problem outside. About 5 years ago, Steve come back to Stanford. He and I have a meeting. We brainstorming a lot of ideas. How do we solve this problem? So we come up strategy. How do we stabilize the interface to overcome the high chemical reactivity problem at the interface? We also point to the community and say not only chemically need to be stable, at the same time mechanically needs to be stable. Otherwise, it's plating and stripping. Keep changing your interface, putting a lot of stress onto your interface. You better find an interface that's chemically and mechanically stable. And after that, we saw it's not enough. Because of this 15 micron lithium plating in and out, it's just too dramatic. We need to build a stable host, hosting metallic lithium inside, and together with a few other strategies. Let me highlight this host idea. What's the host idea? This was done by a graduate student, Ding Chang, who is sitting right there. We want to build a host hiding this metallic lithium into domain inside this red color host. If you strip lithium away, this whole structure remains stable and holding the whole volume right there and make it possible to have an interface you can build. And then when you play lithium, it plays into this host. So Ding Chang developed a very clever concept. So we wanted to use metallic lithium in the molten state, melt the lithium, embed it into a host. We search carbon nanotube film as the host. You see this molten lithium, they form droplets, they don't wet. And we try all types of substrate until we try the reduced graphene oxide. Now you see the lithium melt and wet and go into the structure right away. So we recognize, similar to water, and water we have hydrophobic and hydrophilic to describe whether water can wet a surface or not. Now we invented a new term, we call this as lithophobic or lithophilic to describe the lithium wetting behavior. So the reason graphene oxide can wet is this polar functional group of OH, COOH. Compared to the graphene or regular carbon, you don't have enough of this polar group. The polar group will react with lithium. These protons will be given away. So the reaction of the free energy delta G between lithium and graphene oxide, this surface reaction give you negative delta G, driving the reaction happen. And that really means this lithium metal really like the surface of graphene oxide, cause the wetting phenomenon taking place. We reduce graphene oxide 8% by weight only, stacking into a layer structure by filtration process, and putting into molten lithium. It reacts with molten lithium react with graphene oxide, and generate a little bit of hydrogen bubble. Right, this will open the spacing between the gap, and the wetting happen. The molten lithium will wet into the graphene oxide and hiding now between the two graphene oxide. Graphene oxide in this regard is the whole structure for the lithium metal. And after this processing, this is flexible, just like a metallic foil. So this could be used using the existing battery manufacturing machine. You can process that. So now let's look at the deposition behavior. This is with reduced graphene oxide. After deposition, the surface looks smooth. If you deposit lithium onto copper foil, it forms this dendrite. So we don't have those dendrite formation. This made this lithium foil inside the graphene oxide, a lot more stable, a lot more safer. And as we said, and these type of lithium into the graphene oxide, lithium metal hiding between, you look at the cross section of this whole film, and you strip lithium away completely, it only shrinks its thickness by about 20%. So it's now a lot more stable instead of becoming completely empty. You have a whole structure that could stabilize this metallic lithium. You place it back, it comes back to the initial thickness. Making these plating and stripping, this is the voltage profile. This is a smaller one, tells you it's stable. The blue color is stable. The red color is the regular lithium foil. The voltage open up is telling you you need to use higher and higher overpotential. It becomes less and less stable. So we have now a solution that's a lot more stable. The searching of the host continued. And the last year or two also, after graphene oxide, we have been able to identify a number of very promising host materials. Now, minimize the volume change of the whole electrode. Now it's a virtually zero change. That really provides a stable materials platform. You could now play with interface, make this lithium metal better. So that was the first topic. I want to select the one example to share with you. Now let me come to the second one. So battery seems to be a black box. It has been a black box. It is still to a large degree a black box. Why it can still be working? And we didn't have a full picture of understanding down to atomic scale, how the batteries work. So it's been about more than 10 years. I have been always thinking, can we really, using our TEM, transmission electron microscopy, to look at the batteries? However, for most of the battery materials, that was not so useful because lithium are moving all the time. And these battery materials, you look at the anode, they're so reactive chemically. They react with the moisture, with oxygen, and also their melting point is usually very low. As soon as you focus electron beam onto your battery materials, they evaporate. So it's really hard. Last year, you have seen this announcement. In October 2017, Nobel Chemistry Prize was given to these three gentlemen. They invented, they advanced the cryogenic electron microscopy technique for studying the biomolecule, try to solve the protein structure, for example. The Cryo-EM in the past 10 years has a lot of advancement. It uses liquid nitrogen or other really cold liquid to cool down your biomolecule, make it more stable. And also this very sensitive detector can detect the signal with very small dose of the electron, can already image the protein and DNA, RNA, and so on. And this was the technique my group have been used for about 2 years now. And roughly 2 years ago, I recognized biologists developed such a cool tool. It might be very useful for the battery research. And these two students were the hero. And I talked to them. I said, "You guys stop your current project. Let's work on a Manhattan project, right? Just complete new stuff. I don't know whether it's going to work, but it's worthwhile to spend a year or two of your graduate life with me to explore this area here." Here is what they developed. And we deposit, for example, metallic lithium filament onto a TM grid and put into liquid nitrogen without exposed to air and really cool down this very fast. You stop your chemical reaction in liquid nitrogen. That's at a temperature of 77 Kelvin. And they develop a transfer technique going to transmission electron microscope without exposing to the air, without leaving the liquid nitrogen temperature. So it took them a while to do it. So after several months, we have really surprise data. This is a lithium metal filament. Using this Cryo-EM technique, we could image. In the past, as soon as you image your metallic lithium filament, it look like dark color. The reason is this lithium metal already react with the moisture in the air, even with a second exposure. And that's the end of the world, right? That will cause it become black. That's lithium metal should look like this very light contrast because it's element number 3, small atomic mass. It shouldn't have that much contrast under electron microscope. And this is already become lithium oxide, lithium carbonate. This is the standard TEM. You focus electron beam, you see you drill a hole into this structure right away. So you cannot image them. Now with a cryo-EM, you can look at the structure for 1 minute, 5 minutes, and 10 minutes. They still remain the same. And using an analytical tool called EELS, electron energy loss spectroscopy, we can confirm this is a metallic lithium we are looking at. Instead of lithium ion, it's metallic lithium. This is very exciting image. When my students show to me, I say, wow, this is just amazing. This is first time anybody can see atomic scale image of metallic lithium. Lithium metal is only 180 degrees C, melting point. The bonding between lithium and lithium atom and metallic lithium is very weak. So now it's possible to look at this atomic scale resolution. And now we can even look at along which direction crystallographically metallic lithium can grow. This allows you to study the growth habit, eventually provide information to solve the lithium dendrite problem. We discover along 111 direction, it's 50% of the dendrite like to do so. Along 211, 30%, 110, 20%. This has a reason why along certain direction is more, because the sidewall surface tend to terminate with a particular direction of a crystalline surface, 110. That's the lowest energy surface. That actually can explain this behavior. There's also a long outstanding issue in the battery research field. That could determine the battery safety to a very large degree. That can also determine the battery life, how many cycles you have, how many years your battery can run. That is actually the interface, solid electrolyte interface. There were 2 models proposed in the past couple of decades about what are the structure at the surface, the interfacial layer of these materials. There's a multi-layer model, there's a mosaic model. Mosaic model means in this interfacial layer, you have inorganic nanoparticles of decomposition compound embedded into the organic matrix of polymer. So indeed, under this so-called ECDC electrolyte, we can identify, this is schematic drawing of a nanoparticle of lithium oxide, lithium carbonate, embedded into this green color, amorphous matrix of polymer, decompose and form through this by this electrolyte. We can identify, if you could see this image clearly, a projection in the screen, atomic scale resolution, identify these inorganic particles into organic matrix. However, we have also seen, by adding the additive, so-called FEC, into the electrolyte, we can see the multi-layer structure of SEI as well. In this case, if it's inorganic of lithium oxide on top of the amorphous matrix of this polymer. And these are very 2 different structures of solid electrolyte interface. And this discovery is indeed different from the initial multi-layer model people proposed. Initial people proposed is the inorganic layer is underneath of this amorphous polymer matrix. So we see the opposite. So you say, why this is important? Why this is important? And recent data unpublished yet by my talented graduate students, they're sitting right there. They see these 2 different morphology, and they give you a different interfacial impedance, resistance to the ion movement. That will change how the battery material, such as lithium metal, how they plate, what's their morphology. And that can change the efficiency of the plating and stripping, so-called Coulombic efficiency. That can determine your battery cycling life, can be long or short. So the ability to understand this and to correlate the structure with electrochemical performance, eventually, hopefully, we can design artificially a very nice interface, probably allow us to make the battery run much longer cycle life and calendar life. So I want to touch the third topic about the battery safety. It's still hopeful you can make the battery safe. We know battery inside has organic electrolyte. You have seen the instance over the years, whether it's airplane to the very small phone devices a couple of years ago or Note 7. This happened periodically. Every 2 years or so, you always see a big instance coming in. And this instance usually come from a reason you have a battery cell. It could be external. It could be internal. You have some type of shorting happening. So there's many reasons can cause this shorting. And externally, you have accident. The outside force, bump into your batteries can cause the shorting. Internally, you might have defect. You might have charged your batteries, overcharged. And you might charge in a cold weather, low temperature. And internally can grow a lithium dendrite. No matter what's the reason, this will cause fast release of the battery electricity. The battery started to heat up. At about 100 degrees C, roughly this range, the interfacial layer of your anode will start to have exothermic decomposition. That's why I was telling you as SEI is quite important, this interfacial layer can affect your battery safety and your cycle life. And the temperature keeps going up because you are releasing more and more electricity. About 180 degrees Celsius also. Exothermic reaction between the cathode oxide and your electrolyte start to happen. And this will quickly heat up your battery to 300 degrees C, 400 degrees C, 600 degrees C. This is called thermal runaway. So at this moment, it's very hard to stop. Nearly impossible to stop the reaction. So this thermal runaway can cause the battery catching fires, and the worst cases will be explosion happen. Looking at this issue, we have been trying to come up with a new solution to prevent at each stage of the problem. Let me share with you with 3 ideas. One idea is if you have internal plating of metallic lithium, can you inside this battery separator, this positive electrode cathode, anode, this is separated, the yellow color. In the middle, this red dashed line is a metallic, about 100 nanometer or 200 nanometer, very thin coating, put in the middle. And instead of having 2 electrodes, let's have 3 electrodes for each battery cell. If you have a shorting happening, glow halfway, you detect this middle layer with your anode. You see the voltage goes to nearly 0. That tells you the shorting is coming. It's halfway. You better stop your battery charging and don't use your battery anymore. So make it safe. So that's our solution number 1. These can help addressing the problem of plating. If your battery has manufacturing defect, and that can cause the plating halfway, let's stop using it. The second one is, what if you cannot prevent that? Your battery has to heat up. Then you need to have a fire extinguisher mechanism going in. And we can put fire retardant encapsulated into this polymer, for example. And you can put in this green color, fire retardant encapsulated into the polymer. The polymer's melting point can be engineered to the temperature you want. For example, 100 degrees Celsius, around that. If you get to that temperature, the polymer melts and then release this fire retardant. So you can prevent a battery catching fire. We have also worked with Professor Zhenan Bao in chemical engineering to say, well, let's find a switching mechanism to make the battery safer. If you have a shorting happening in one of these current collector, we have a polymer layer with a nano spike of nickel embedded inside. At room temperature, it's conducting. But if your battery heat up to high temperature, this polymer volume expand and pull the nickel nano spike, a lot of this particle open. So the whole layer become an insulator. Make the release of the electricity very hard, so you don't heat up your battery that much. You have a thermal switching, can control that to about close to 100 degrees Celsius also. And this electroconductivity going from metallic to insulator at a controlled temperature. So in a small cell, the three mechanisms work reasonably well now. We try to explore this for the large cell used in your phone and your car. And these three ideas adding together might make your battery much safer. I'd like to come to the fourth topic, grid-scale storage. This is completely different. Grid-scale storage compared to the transportation batteries, it does not require high energy density. In principle, it does not require. But you cannot also go to actual small energy density. It won't work from the cost consideration. Also from the consideration of the real estate, the land it occupies, it will not work either. You still need certain energy density. I want to share with you a couple ideas on this topic. We know grid-scale energy storage is so important for us to integrate solar and also wind into the electrical grid. It helps us to stabilize the grid for us to have a much smarter grid. At Stanford right here, we have bits and watts initiative. It's exactly try to dealing with, to reconsider how we do the grid. For the grid-scale storage, this opportunity for the batteries to contribute to smooth out the fluctuation from seconds to minutes to hour, and also to do the peak shifting, store electricity when there's a lot of generation, not that much use, and then use it later when you have a peak use, and from hours to day. And also seasonal storage. We have a lot of solar during the summertime, but not in the winter time. And certainly seasonal storage is a lot harder. The easier one to start with could be these seconds to minutes to hours. The more cycle of the battery you use, the better for the batteries in terms of the cost consideration. Seasonal storage, you use it about 1 to 2 cycles per year. So that's not a good use of your battery from the cost. Probably the largest application is in the peak shifting. Let's look at the current storage. It's still the pumping the water. It's the most low-cost one for storage. And due to the elevation difference, pumping it during the electricity storage and use it and then flow the water down. This has the location dependence. Getting the permit will be very hard. This has limited use right there. Let's look at the grid scale storage. How big of scale that could be? Several years ago, when I gave the talk right here in the energy seminar, our annual production of lithium-ion battery is only about half of this size. 2017, the data will come out soon, but I will predict it's about double, about 4 years ago, 70 gigawatt hour. But in California alone, for grid scale storage, we probably need 50 gigawatt hour easily. We need that. And you put the whole year production, it just barely can satisfy a California need for the lithium ion. And how many batteries we need right there? We need this Stanford Stadium, the football stadium, filled to half of these batteries. That will be sufficient for us to use. It's a big problem. So this idea, can we consider different idea for the storage? If you look at now, what are the options? Actually, lithium ion still a very strong contender. With the cost going down so fast, no other batteries have lithium ion's performance and cost yet. Lead acid is a very low cost. However, lead acid only have 3 to 4 years lifetime, and lithium ion is longer. And flow battery has been considered is this liquid. consists of redox molecules. You can charge up this redox molecule by flowing one way and discharge and flow it back. Vanadium redox is well known. At this moment, it's still high cost. Membrane cost right here is very important. That's an ion selective membrane. Doesn't allow the redox these ions to go through, but only the protons. It's high cost. And also the energy density is low. For this redox molecule, solubility is not enough. You're talking about 30 watt per kilo. That's about 7 times lower than lithium ion. With all the controlling electronics going in, the system level cost, lithium ion now is about 250 watt per per kilowatt hour, 250. And a redox flow is about 400, 500 range. It's still too high. So if you could increase the energy you store, you can reduce the cost. A number of years ago, we showed lithium polysulfide has much higher solubility, and compared to vanadium, that's 1.7 molar, and lithium polysulfide can have even 5x more. So you increase the amount of energy you store, you reduce the cost. And we invented this technology with a metallic lithium anode. So you have a solid, you have a liquid. They react by themselves, forming this self-decomposition compound, the SEI. That's your membrane. So you don't have to use other membrane. You reduce the cost. These still remain as a very attractive idea of a semi-flow batteries for the grid-scale storage. We show these can cycle for 1,000 cycle type of range, still going. I also want to highlight in the last year or two, my group just started a new project and looks very promising. Wei Chen is a postdoc in the group working on this project. And we look at what might be the possible choice. It turned out to be these could be an attractive solution for grid scale. It's a nickel hydrogen gas batteries. Let me clarify, it's not nickel metal hydride. It's a nickel, the same as nickel metal hydride, but the hydrogen is different. Nickel metal hydride using hydrogen stored in the alloy. Here we only use gas. And basically if one is solid electrode, that's a nickel oxyhydroxide and nickel hydroxide cycling back and forth during charging. But the anode is hydrogen and water. And building up this battery is simple. So it's taking the nickel hydroxide and water and putting the catalyst for the hydrogen into this electrode. You build it up in the discharge state. Once you charge it up, you generate hydrogen gas and put it into a tank. So it's also an idea of semi-flow battery. Half is solid, the other half is gas. You only flow the other half. Very simple construction. And this has the very long cycle life. These show you more than 1,200 cycles without decay. It's about 1.3 watt aqueous solution batteries, very low cost. And these have shown this quite amazing performance. For aqueous system, this can potentially get up to 130 watt per kilogram. And lead acid is only 30-40. The usual redox flow is about 30-40. This you are talking about 3 times higher. And the volumetric it's not bad. The key thing is we think the cycle life can go to 10,000 cycles. We have done the limited a couple thousand cycles, virtually without decay. And this is extremely important. Calendar life could be 25 years. How do I know that? After we invented this, Wei and I searched in the literature. We say, let's see whether people have worked on this before. It turned out to be a few decades ago. And NASA used this chemistry for the satellite. So you go to the satellite. If you don't have 25 years, you are not allowed to get into satellite. But why did we forget about this battery chemistry? That's because at that time, the anode part, using platinum as catalyst, that's high cost. Now we have different catalysts for our hydrogen electrode, made the whole batteries much lower cost. These can potentially get down to these $50 per kilowatt hour type of range. So this offers a very attractive solution for grid-scale storage. Eventually, we are looking for $100 per kilowatt hour. So this is a good starting point. In the last few minutes, let me mention the issue of the resource availability for the batteries. Let's mention the lithium first. I showed some of this slide before. We have 40 million tons of global reserve for lithium. This is going up, this number. Is this enough? Are we worried about the availability of lithium? So let's do a little bit of analysis. This 40 million ton is enough for us to make a 10 billion Nissan Leaf. And if you drive Tesla, that will give you 3 billion Tesla. That sounds still not enough, right? We have about 1 billion cars running in the world right now. But don't forget, we have virtually infinite amount of lithium in the ocean. Indeed, looking at this number, Steve Chu and I recently started a project to extract lithium out of the ocean. And now it looks quite promising. And we could do that. We can beat sodium chloride in the ocean and take lithium out. And the cost is not quite meeting the cost of from this reserve yet. But as long as the lithium concentration increase slightly, and it doesn't need to be those very salty lakes having a lot of high lithium concentration, just a little bit higher than the ocean, we will be economically viable. So I think this issue potentially can be solved, the availability of lithium. But I do want to point out, what are the possibilities for the grid scale with the current lithium reserve. Our electricity consumption about 5 terawatt, maybe a little bit higher now. To store 4 hours of the electricity of the whole world, we need about 16 terawatt hour of batteries. And our 40 million ton is enough for us to make 240 terawatt hour. In that regard, we still have a lot of lithium. But I still need to warn you, lithium is not just used for batteries. It's used for aircraft as well. It consumes a lot more lithium than a battery to make lightweight alloy. So let me show you how sensitive the lithium price could be. In the last several years, starting from 2015, China announced electric car, significant support for the electric car program. And the lithium price go up tremendously after that. And there's a large number of electric cars sold in the past couple of years. You can see 5x price increase. We are still not running the shortage of lithium yet, but these demand and supply issue can drive the price in a very sensitive way. Let's also looking at the issue of other important elements inside the batteries. Anode using graphite, cathode and the current technology using lithium cobalt oxide, lithium cobalt nickel manganese oxide. Let's look at the cobalt price. And 2017, that's right there, you see the price rise 3.5x, reaching $35 per kilogram. This price is too high. That's why you see recently all the battery companies say, let's go to high nickel MMC. Let's don't use that much cobalt because the cobalt is too expensive. We have limited availability of cobalt. That become an issue. Nickel price is about $6 per kilo. Not that expensive yet. But once we go to the large deployment of electric car and moving into the grid using these materials, and the nickel's availability, the price, could become an issue as well. Also watch for the copper. We use a lot of copper foil for the anode. If we use a lot more copper, we also need to watch that as well. So with that, we say, what is a strong motivation? Let's don't use those metal. They can be expensive. They have limited availability. Developing a lithium sulfur chemistry becomes attractive. Sulfur is everywhere. I believe this is a mountain of sulfur in Canada. So you don't know what to use this for. It's just pile right there. The cost is less than $1 per kilogram. So it's so much cheaper. And this can offer you lithium sulfur chemistry, can offer you practically, perhaps in the future, 3 times of the energy density compared to current technology. So I also want to touch upon lithium battery recycling. This is the lithium cost, this is the cobalt cost. You look at its basic structure. What are the valuable stuff inside the batteries? From anode, the copper foil. Copper is valuable. We want to take the copper out. Graphite particle. Perhaps you don't need graphite. Graphite we have a lot more. They are not worth to be recycled. Your separator is just polymer, polyethylene, polypropylene. So you can burn it. That's probably fine. And lithium cobalt oxide, right, has cobalt. This can have lithium nickel oxide, have nickel. This needs to be recycled. They're high cost stuff. And then aluminum foil, aluminum is cheap. That's okay if you don't recycle that. So these are the valuable stuff. In order to cycle your lithium back, you don't want your lithium and the charge state going to anode. You actually want it to return all the way back to the cathode. They store in the lithium cobalt oxide. Then you recycle cobalt and lithium together, right? So if you look at the existing battery recycling technology, this is the one. First of all, when you collect these batteries, it might not in a discharge state. It could still have a lot of electricity right there. It could be dangerous. It's a bomb. So let's discharge that first. But you don't want to have a robot or individual to go connect it and short the batteries. So that costs too much. And the idea is, actually people are smart. They throw it into the salty water. The salty water conduct electricity. You throw all the battery inside, right? And then you can discharge that after 25 hours. This part is easy to do, but the next part is so much harder. So how do you recycle that? Once you look at that, you say, well, don't forget about it. Don't look at it, right? So it's just too many steps. The cost is too high. The rough idea is you take the batteries, and then you break them into small pieces. And then you leach out lithium, cobalt, nickel, and then you separate them and take them out. You use strong acid, and you consume a lot of energy to recycle them. And the cost is too high. There's no good way to recycle the batteries yet. I challenge my student and also all the students sitting right there. You guys need to think about how to recycle batteries. This problem is coming very fast, right? Tesla's car, the first batch in a few years will retire. This huge number of batteries will be recycled. We need to figure out this problem soon. There's a couple more questions I want to answer very quickly. We'll end my talk. So what about all solid-state batteries? If you do that, you make them safer. In principle, yes. Solid-state can use ceramics. In the past several years, a lot of progress made. People know how to make solid-state. The ion conduction in solid-state very fast, as high as liquid and even higher than liquid. So that's great. The challenging is interface, how to combine solid-state with all this volume expansion without cracking. And also the solid electrolyte is very brittle. If you use ceramics, if you use polymers, certainly that's better. But polymers' ionic conductivity needs to be improved. So still quite early. We will not be able to see solid-state batteries and deploy in a significant scale and anytime very soon. What about fast charging? How fast can you do that? So what's the fast charging problem? You have anode, you have cathode. If you do fast charging, you push lithium ion electricity too fast. These graphite anode will not be able to take it, the lithium, so fast. And there's also a term called overpotential is too high. You go through go below the 0 volt versus lithium. You are going to plate out lithium dendrite. It will grow a dendrite and show your batteries. That's very challenging. So people have not figured out yet with fast charging. Unless you use other anodes such as lithium titanium oxide, the voltage is very high. And for the anode, the potential, you can do fast charging, less than 10 minutes. But you also lose half of your energy density because your anode potential is too high, your full cell voltage is about half. So how do you maintain reasonably high energy and do fast charging? We don't know how to do. And Department of Energy recently has a proposal called asking for idea how to solve this problem. So we'll see whether great ideas can come. What about swapping the batteries? Is this still a viable approach? If we have too many electric cars on the road, we don't have fast charging. Our real estate price in Palo Alto and San Francisco will be too high. We probably want to figure out fast charging or some type of swapping batteries. And the swapping battery, I think this idea is still not dead. When I talk to the companies in Beijing, they say Beijing real estate price is so high, there's no way they can, having so many cars, swapping ideas, this idea might be coming back. So what about other things? Sodium, magnesium, aluminum batteries, you heard a lot about this, right? In the papers, in the news. This is very exciting fundamental research right there. You have to remember, sodium ion is bigger than lithium, so that's a little harder to move sodium. Magnesium is 2+, aluminum are 2+, they're harder. But they do offer the potential. Sodium, magnesium, aluminum, they're a lot cheaper. What if the lithium become a problem? Then you should have this as a backup. I think we should do that. We should have fundamental research working on this. But the challenging right there, make sure you have to have the right cathode, right anode, right electrolyte, and salt, the whole system for all these new chemistry. They are not there. And this could take many years before we get there. So for the next 10 years or longer term, for transportation, it will be mainly the world of lithium-based batteries. Will be half of sodium, magnesium, aluminum to come in to make an impact. It will be still lithium. And there's a lot of room to improve. The issues I already mentioned. And the opportunities there, energy density, cost, life, safety, resource availability, recycling. And grid-scale storage, the opportunity are wide open. There's not a winner yet for the grid-scale storage. It might be lithium. With such a portable electronics driving force, electric car driving force, perhaps the lithium will go down to the cost very fast and get to the grid scale. Flow battery has a shot. And our new nickel hydrogen gas battery, this might be the one. The new chemistry showing great potential. This other aqueous solution battery also show, based on sodium ion, for example, might have the great potential. Well, let me end my talk by thanking the whole research group, the support from many of my collaborators over the years, and also locally, many of you have been either cheerleaders, and for example, GSAP have providing a lot of funding over the years. And thank you very much for your attention. I will be happy to take any questions you have.
Yeah, unfortunately, we're going to have to give up our AV equipment. We could take questions after. Let's take one or two very quick questions. Any student questions? Yes, sir. Thank you.
Thank you for really enlightening talk. I have a quick question regarding the semi-low battery for the polysulfide you mentioned about. What are the major challenges you currently observe for the grid scale deployment for this type of technology?
There are majorly two. The first one is we still use the solvent that's flammable, either base solvent. They can burn easily and catch fire. The second one is related to performance. The Coulombic efficiency is not high enough yet. We still lose lithium each cycle. In order to get to a long cycle life, calendar life, with a limited amount of lithium metals to start with, we still need to solve that problem. Mm-hmm.
The target energy density of a battery ideally should go up by 2.5 to 3 times compared to today, and yet the charging rate is hoped to go down by an order of magnitude. But nowhere did you reference any operating temperature inside the medium of the battery, which I imagine without proof can be fairly high. So now that's that's a question. I think that the temperature issue has to be addressed, which apparently is not yet. Secondarily, the addendum question has to do with the usefulness of using Cryo-EM to look at battery structure. I can imagine that Cryo-EM is sort of okay, to do post-accident analysis, but yet what the image structure doesn't replicate the structure at the time of failure because of thermal conditions, such as thermal motions and etc. etc. So what's the use of Cryo-EM for imaging, given those circumstances?
Yeah. So first question is the inside the temperature of the batteries when you do fast charging. That is an issue, absolutely an issue. If you do fast charging, we all know if you do fast, the battery's cycle life will be shorter because there's a lot of bad things happen. We don't know how to solve that yet, so that needs to be done. But I also take that as an opportunity. Maybe a great idea is if you want to do fast charging, try to tune your electrolyte. Fast charging at elevated temperature, the kinetics go very fast. Allow you to do fast charging, that might be an opportunity. So the second question is the Cryo-EM. Looking at the frozen structure, how do you use that to represent the dynamic process inside the battery? That's the essence of your question. What we could do is, at a different stage of operation, you freeze that fast, you freeze that snapshot, and then put it into the TEM, the Cryo-EM, to look at it carefully. Now, and you freeze in the different stage, allow you to build up a kind of a semi-video to reflect what's happening. That would be my answer. Yeah.
Great. Let's thank Guy one more time.